January 17, 1945, somewhere over the frozen Rhine Valley. The cockpit trembles, metal groans beneath the weight of altitude and purpose. Through the frost-glazed canopy, a B-24 Liberator crew watches the Earth below, a patchwork of white fields and skeletal forests stretching toward the industrial heart of the dying Reich. The bombardier hunches over his Norden bomb site, hands steady despite the flak bursts blooming like black flowers in the sky around them. But today, something different rides in the bomb bay, something the men don't fully understand themselves. They've been briefed on the new equipment, radio-controlled guidance systems, transmitted signals, frequencies that can bend the path of a falling bomb through invisible commands carried on electromagnetic waves. To the young lieutenant from Ohio, it sounds like something from the Buck Rogers serials he watched as a kid. To the Germans waiting below, it will sound like witchcraft. Far beneath that aluminum bird, in a reinforced bunker outside Koblenz, Oberst Friedrich Hartmann adjusts his field glasses and studies the contrails scratching white lines across the grey January sky. He is 43 years old, a veteran of 2 wars, a professional soldier who learned his trade in the trenches of the Western Front, when radio itself was barely more than spark-gap Morse code tapped out in desperate military shorthand. He has seen technology evolve, watched the Luftwaffe rise from nothing to become the most feared air force in Europe, witnessed the development of radar, experienced the brutal efficiency of coordinated mechanized warfare. But what he is about to witness will shake the very foundations of his understanding of what is technologically possible, what America has quietly achieved, while the Reich poured its scientific genius into rockets and jets and wonder weapons that arrived too late and in too few numbers to matter anymore. The war has reached that peculiar stage where outcome is no longer in doubt but suffering continues regardless, where the Wehrmacht fights not for victory but for something more abstract, duty, homeland, the desperate hope that prolonging the agony might somehow result in a negotiated peace rather than unconditional surrender. Hartmann knows this, though he would never speak it aloud. He has seen the intelligence reports, the grainy reconnaissance photographs showing American factories stretching to horizons, assembly lines producing tanks and aircraft at rates that seem to mark the laws of industrial capacity. He has read the interrogation transcripts of captured American airmen, young men often barely out of boyhood who speak casually of abundance that sounds like fantasy, unlimited fuel, bombs stacked in depots like cordwood, replacement aircraft arriving faster than they can be destroyed, crews eating steak and ice cream at bases in England, while German soldiers gnaw on black bread and stretch their rations thinner each week. But still, there are limits. There must be limits. Physics does not care about industrial capacity. A bomb falls according to ballistic trajectory, subject to wind and gravity, and the inevitable imprecision of release mechanisms. This is fundamental. This is unchangeable. The Americans may have numbers, but they cannot repeal the laws of nature. A bomb once dropped belongs to gravity and chance. This is what Hartmann believes. This is what every Luftwaffe officer, every Wehrmacht general, every engineer and scientist in the Reich accepts as self-evident truth. And this is what is about to be shattered. The first bomb falls at 1300 hours. Hartmann sees it, a dark speck detaching from the formation, beginning its arc earthward. He tracks it with professional interest, calculating angle and trajectory, estimating impact point. The bridge. They are going for the railway bridge again, the one that spans the Rhine and carries the vital supply lines feeding what remains of German forces in the west. They've tried before, waves of B-17s and Liberators hammering away with 1,000-pounders, cratering the riverbanks, collapsing approach ramps, but never quite achieving the precision needed to drop a span into the river. Bridges are difficult targets, narrow and linear, requiring accuracy that high-altitude bombing cannot reliably deliver. The Americans know this. They compensate with volume, sending dozens of aircraft to carpet an area in the hopes that statistical probability will grant them a few direct hits. It is wasteful but effective in its way, a brute force approach that matches everything Hartmann has learned about American military doctrine. But this bomb does not fall like the others. Halfway through its descent, it adjusts. The trajectory shifts, a small correction that no ballistic object should be capable of making. Hartmann blinks, uncertain if he's actually seen what his eyes report. He refocuses the field glasses, searching for the bomb against the grey sky, and there, another correction. The bomb is maneuvering, impassably, undeniably maneuvering. The dark shape carves a gentle curve through the air, responding to forces that should not exist, following a path that violates everything Hartman understands about ballistics and gravity and the fixed nature of falling objects. The impact comes precisely on target. The center span of the bridge erupts in a fountain of concrete and twisted steel, the blast so perfectly placed that the structure's collapse seems almost choreographed. Girders folding inward, roadbed crumpling, the entire center section dropping into the Rhine with mathematical precision. A direct hit, not approximate, not close enough, perfect. Hartman lowers the field glasses. His hands, he notices with distant surprise, are trembling. Around him in the bunker, other officers stare upward through observation slits, faces blank with incomprehension. Someone speaks in German, voice hollow and questioning, asking what they just witnessed, but Hartman has no answer. He served on the Western Front in 1917, survived artillery barrages that churned the earth into moonscapes of mud and corpses, watched men die in clouds of poison gas and mechanical slaughter that seemed to represent the uttermost limit of technological horror. He learned then that war is ultimately about resources and will, about which side can endure the most suffering and continue functioning. Technology matters, but it is merely a multiplier of existing capacity, not a transformer of fundamental reality. But if a bomb can be steered through the air by invisible signals, if precision can be achieved through remote control rather than mechanical aiming systems, then what other certainties are about to crumble? If the Americans have solved this problem, a problem German scientists insisted was decades away from practical implementation, then what else have they achieved in their vast industrial laboratories, their university research facilities, their sprawling military-industrial apparatus that operates on scales the Reich cannot match? The radio-controlled bomb was not a singular revelation, but the culmination of a journey that began years earlier, in laboratories and proving grounds scattered across the American homeland, pursued by engineers and physicists who approached the problem of aerial bombardment with characteristic American pragmatism. If accuracy cannot be achieved through mechanical means alone, then add electronics. If human pilots cannot deliver precision at high altitude under combat conditions, then augment them with remote guidance systems that function despite flak and fear and the chaos of air combat. The Germans had explored similar concepts. The Henschel HS-293 glide bomb entered operational service in 1943, guided by radio commands from the launch aircraft, achieving notable successes against Allied shipping in the Mediterranean and Atlantic. The Fritz X armor-piercing bomb, radio-controlled and deadly, sank the Italian battleship Roma and damaged several other major warships. German engineering had pioneered remote guidance, proven the concept in combat, demonstrated that bombs could be steered through radio signals transmitted from operator to weapon. But the Germans had focused their guided weapons on anti-shipping roles, attacking large, slow-moving targets on featureless ocean backgrounds where an operator with a joystick could track the weapon visually and make corrections in real time. The idea of guiding a bomb against land targets from high altitude, through clouds and smoke, and the visual chaos of industrial landscapes, seemed impractical, requiring guidance systems too sophisticated for the technology of the era. The Americans looked at the same problem and reached different conclusions. They had the industrial capacity to experiment, to fund multiple parallel research programs, to tolerate failure and iteration in ways that the resource-constrained Reich could not afford. They had electronics industries producing radio equipment at scales that dwarfed German production, expertise distributed across universities and corporations that could be mobilized and coordinated through the peculiar American genius for large-scale project management. And they had a philosophical approach to technology that differed fundamentally from German engineering culture, less concerned with elegant theory and more focused on practical solutions that worked reliably in the field, even if the underlying mechanisms were crude or inelegant. The result was a constellation of programs: Project Aphrodite, which packed war-weary bombers with explosives and guided them into hardened targets via radio control; the VB-1 Azon bomb, which added radio-controlled tail surfaces to standard 1,000-pound bombs, allowing bombardiers to correct for wind drift and improve accuracy against bridges and viaducts; the VB-3 Razan, which added range correction to the azimuth control of the Azan, creating a weapon that could be steered in 2 dimensions throughout its fall. These were not wonder weapons in the German sense, no revolutionary physics, no exotic fuels, no barely understood phenomena pushed to their technological limits. They were engineering solutions, practical applications of existing radio and electronics technology, designed to be manufactured in quantity and used by ordinary crews with minimal additional training. Oberst Hartmann did not know these details in January 1945. He did not know about the testing programs at Eglin Field in Florida, where technicians refined guidance systems under sunny skies far removed from the desperation of the European War. He did not know about the production facilities turning out radio-controlled bombs by the hundreds, about the doctrine being developed for their employment, about the training programs teaching bombardiers how to steer falling bombs through toggle switches and radio transmitters. What he knew was the evidence before his eyes: American bombs maneuvering in flight, achieving precision that should not be possible, destroying targets with efficiency that transformed the calculus of aerial bombardment from statistical approximation into surgical certainty. Over the following weeks, the attacks continued. Bridges collapsed under precisely placed explosives. Railway marshalling yards suffered hits that severed critical junctions rather than merely cratering random sections of track. Supply depots erupted as bombs found ammunition bunkers rather than scattering across empty ground. The Wehrmacht's intelligence services scrambled to understand what was happening, capturing unexploded ordnance and discovering the telltale modifications: enlarged tail sections containing radio receivers and servomotors, antennas protruding from bomb casings, electrical wiring that had no place in conventional munitions. German engineers examined the captured equipment with mixed admiration and despair. The technology was not revolutionary, nothing that German scientists didn't understand in theory, but the implementation, the scale, the casualness with which the Americans deployed these weapons as if they were routine rather than extraordinary, revealed a gulf in industrial and scientific capacity that statistics alone could not fully convey. Lieutenant James Morgan flew his 32nd mission in March 1945, guiding Azan bombs against a viaduct in the Ruhr Valley. He was 23 years old, a mathematics major from MIT whose professors had been recruited into weapons development programs and who had encouraged promising students to volunteer for technical military roles where their education might contribute to the war effort. Morgan had expected to spend the war doing calculations in some rear echelon office, applying his knowledge of differential equations to trajectory tables or fire control systems. Instead, he found himself in a bomber crew, operating equipment that seemed to vindicate every optimistic claim about American technological superiority he'd heard in training. The Azan system was ingenious in its simplicity. The bombardier watched the falling bomb through a specialized telescope sight, tracking a bright flare installed in the weapon's tail. If the bomb drifted left or right of the target, pushed by wind or misaligned by imperfect release, the bombardier transmitted corrective signals via a radio transmitter installed in the aircraft. The bomb's receiver picked up these signals and activated servomotors that adjusted control surfaces in the tail assembly, steering the weapon back toward the intended trajectory. It required skill and practice. The bombardier had to anticipate wind effects, judge distances accurately, make rapid corrections while accounting for the bomb's increasing velocity and decreasing response time as it accelerated toward impact. But the principle was sound, and with training, bombardiers could reliably achieve accuracies measured in tens of feet rather than hundreds of yards. Morgan remembers the strange satisfaction of it, the way guiding a bomb felt less like random destruction and more like solving a physics problem in real time. Observe, calculate, correct, repeat. The flare-bright tail of the Azan traced a path through the air that he could adjust with toggle switch commands, each input causing the bomb to shift incrementally, converging on the target through a series of corrections that felt almost conversational, a dialogue between bombardier and weapon conducted in radio pulses and observed motion. When the bomb struck precisely on target, when the viaduct's central pier erupted and the spans collapsed into the river valley, Morgan felt something that surprised him. Not triumph, not vengeance, but a kind of intellectual pleasure. the satisfaction of technique correctly applied, of theory proven through practice. His German counterparts felt something entirely different. Hauptmann Klaus Richter, a Luftwaffe officer tasked with analyzing American bombing patterns and developing countermeasures, sat in his office in a requisitioned schoolhouse outside Frankfurt and studied reconnaissance photographs that documented the increasing precision of American attacks. The images told a story that he found profoundly disturbing, not because of the physical damage. The war was lost regardless, that much was clear, but because of what they revealed about the nature of American power. The Reich had prided itself on technical sophistication, on scientific advancement, on the engineering genius that produced jets and rockets and weapons that seemed decades ahead of Allied equivalents. But precision bombing via radio control revealed a different kind of advancement, one that depended not on individual breakthrough technologies, but on systematic excellence across multiple domains: electronics, manufacturing, training, logistics, doctrine. Richter had read the intelligence assessments estimating American production figures, numbers that seemed physically impossible, until you examined the photographic evidence of factory complexes that stretched for miles, of shipyards launching Liberty freighters and escort carriers on assembly line schedules, of bomber formations so large that they took hours to pass overhead. The Reich had marshaled its resources brilliantly in some ways, achieving remarkable things through focused effort and theoretical excellence. But America marshaled resources on a scale that transformed quantity into its own kind of quality, that allowed for parallel development programs and redundant research paths, and the tolerance for failure and iteration that breakthrough innovation often requires. The radio-controlled bombs were emblematic of this approach. They weren't revolutionary weapons that would suddenly reverse the course of the war. They were incremental improvements, pragmatic solutions to specific tactical problems, deployed in sufficient numbers to make a strategic difference precisely because America could afford to manufacture thousands of guidance systems and install them in bombs that might miss or malfunction or be jammed by countermeasures. The Germans had developed guided weapons too, but they deployed them in dozens or hundreds, hoarding them for critical targets, unable to sustain the production and technical support that widespread use required. America simply built more, trained more crews, accepted losses and imperfections, and relied on volume and persistence to achieve effects that German precision engineering could not match. Richter wrote in his assessment report, a document that would be captured by American forces weeks later and filed among thousands of other intelligence materials, that the radio-controlled bombs represented something more threatening than any wonder weapon the Reich had produced. They represented a philosophy of warfare that the Wehrmacht could not counter because it required resources and industrial capacity that Germany simply did not possess. You could shoot down the bombers, jam the radio frequencies, develop new tactics and countermeasures, but you could not compete with an enemy who could absorb those losses and countermeasures and simply produce more systems, train more crews, iterate and improve through successive generations of equipment while maintaining offensive operations continuously. It was less like fighting an army and more like fighting an industrial process, one that ground forward regardless of tactical setbacks because strategic capacity was effectively unlimited. The psychological impact of the radio-controlled bombs extended beyond military circles. German civilians, already reeling from years of strategic bombing, found this new precision particularly unnerving. When bombs fell randomly, when entire neighborhoods vanished under carpet bombing raids, there was a kind of terrible democracy to it. Everyone was equally vulnerable, survival was a matter of chance, and you could take grim comfort in the randomness of fate. But when bombs began hitting specific buildings, when command posts and communications centers and supply dumps were destroyed with what seemed like malicious intent, it suggested a level of American omniscience that was psychologically destabilizing. They knew where targets were. They could hit them precisely. The illusion of safety that distance or camouflage might provide evaporated. The Americans saw everything, and what they saw they could destroy. This perception was amplified by German propaganda, which had spent years insisting that American forces were technologically inferior, dependent on quantity rather than quality, lacking the scientific sophistication and engineering excellence that German industry represented. When reality contradicted these narratives, when American equipment proved not just abundant but genuinely superior in practical terms, The cognitive dissonance was profound. How could a nation of capitalist shopkeepers and immigrant mongrels, a society supposedly softened by democracy and decadent individualism, produce weapons systems that German engineers studied with envious admiration? The contradiction suggested fundamental miscalculations about the nature of American society, about the relationship between democracy and technological innovation, about whether authoritarian efficiency could actually compete with decentralized creativity operating at continental scale. The radio itself became a symbol in this transformation of perception. To the Germans, radio had been a tool of control. Goebbels used it to broadcast propaganda, unifying the Volk through centralized messaging. German military radio doctrine emphasized secure communications and command authority transmitted downward through hierarchies. Radio was about control, about imposing order through electromagnetic means. But the Americans used radio differently, not just for communication, but for control of physical objects, for precision guidance, for extending human capability into machines that operated semi-autonomously under remote direction. It represented a fundamentally different relationship with technology, one that emphasized augmentation over control, networked systems over hierarchical command, distributed capability over centralized authority. American bombardiers like Morgan understood this intuitively, though they would not have articulated it in such terms. They experienced radio guidance as a tool that made them more effective, that allowed their training and judgment to achieve results that mechanical systems alone could not deliver. The bomb became an extension of the bombardier's intention, responding to inputs that corrected for conditions that no automated system could fully anticipate. It required trust that the technology would respond as designed, trust that the radio signals would reach the weapon through jamming and interference, trust that the enemy could not exploit or corrupt the communication. This trust was earned through training and repeated success, through systems that worked reliably even under combat conditions, through an engineering culture that prioritized field performance over theoretical elegance. By April 1945, as American forces drove deeper into Germany and the Reich collapsed into fragmented chaos, radio-controlled bombs had become routine, just another item in the aerial arsenal alongside conventional munitions and incendiaries. Their novelty had worn off, replaced by professional acceptance of tools that worked reliably and delivered results. For the men who deployed them, the radio-controlled bombs were simply better equipment, another example of American industrial might translating into battlefield advantage. The wonder and fear they had initially inspired faded into routine, which was perhaps the most damaging psychological blow of all. That weapons which should have been revolutionary were instead merely standard, that American technological superiority was so overwhelming that the extraordinary became ordinary through sheer abundance and systemic excellence. Friedrich Hartmann survived the war. His bunker outside Koblenz was abandoned in March as American forces encircled the Rhine Valley, and the Wehrmacht conducted its final, futile retreats eastward. He surrendered to American troops in Bavaria in May, joining millions of German soldiers who transitioned from combatants to prisoners in the span of a few exhausted weeks. The interrogation teams that processed him were interested in his observations of American bombing tactics, and he told them about the radio-controlled weapons, about the impossible precision of bombs that steered themselves through the air. The American officers nodded and took notes, but seemed unsurprised, as if guided bombs were merely one item on a long list of technical capabilities that they took for granted. What struck Hartmann most forcefully during his imprisonment was not the treatment he received. The Americans were professional and generally correct in their conduct, but the evidence of abundance that surrounded him even in captivity. The POW camp was supplied with a casualness that would have seemed fantastical to German logistics officers. Food arrived in quantities that allowed prisoners to eat until satisfied, a luxury that Wehrmacht soldiers had not experienced in years. Medical supplies were sufficient to treat minor ailments and injuries that German forces would have ignored as not worth the expenditure of scarce resources. The American Guards carried equipment that was clearly mass-produced, yet of good quality, weapons and radios and vehicles that showed no signs of material shortage or manufacturing compromise. One day in June, Hartmann watched as a cargo plane flew overhead, heading toward the interior of Germany with supplies for occupation forces. He counted the aircraft visible in the sky, 7 within his field of view simultaneously, a density of air traffic that represented logistical capacity beyond anything the Luftwaffe had maintained even at its peak. The Americans were supplying occupation zones in a defeated enemy country with more efficiency than the Wehrmacht had managed to supply its own forces fighting for national survival. The contrast encapsulated everything he had come to understand about the war's outcome. Germany had lost not because its soldiers lacked courage, or its generals lacked skill, or its scientists lacked genius, but because it had fought an enemy whose industrial and technological base operated on a scale that rendered traditional military virtues insufficient. You could not bridge the gap through tactical excellence or operational brilliance or technical innovation in specific domains. The gap was systemic, extending across every aspect of national power, and the radio-controlled bombs were merely one visible manifestation of a deeper disparity. The technical specifications of the radio-controlled bomb programs reveal the characteristic American approach to weapons development during the Second World War: practical, iterative, focused on field deployability rather than theoretical perfection. The VB-1 Azan, the most widely deployed radio-guided bomb of the war, was essentially a standard AN 64,000-pound general-purpose bomb fitted with a modified tail section containing a radio receiver, a battery, and servomotors that controlled movable tail surfaces. The guidance system operated on a frequency of 475 kHz, transmitting simple commands that the bomb's receiver decoded into discrete adjustments: left, right, or neutral. The bombardier tracked the bomb visually using a telescope sight and tapped a telegraph key to transmit steering corrections, watching the flare in the bomb's tail shift position in response to the commands. The system's simplicity was its strength. There was no complex computation, no sophisticated feedback mechanisms, no requirement for advanced electronics that might be unreliable under combat conditions. The bombardier provided the intelligence, observing and correcting through repeated inputs that guided the weapon toward its target. The bomb itself was relatively dumb, capable only of responding to discrete commands without any autonomous behavior or programmed intelligence. This division of labor, human judgment for strategy and real-time correction, machine precision for execution of commands, would become characteristic of American military technology development, leading eventually to the sophisticated drone systems and precision-guided munitions of later eras. But in 1945, it was simply a pragmatic solution to the problem of improving bombing accuracy against point targets. Production figures for the Azan system illustrate the American capacity for manufacturing new technology at scale. Between 1944 and the end of the war in Europe, approximately 15,000 Azan guidance units were produced and installed in bombs. Not all were used. Many remained in inventory when the war ended, but the scale of production meant that American bomber crews had sufficient numbers to use the weapons routinely rather than hoarding them for critical targets. A bombardier could expend multiple Azan bombs on a single mission, accepting that some would miss or malfunction, secure in the knowledge that more were available for the next mission. This abundance of precision-guided weapons represented an approach to warfare that the Germans found difficult to comprehend. The Americans simply built enough of everything to tolerate waste and inefficiency at tactical levels while maintaining strategic effectiveness through sheer volume. The Razan bomb, developed as an improved version of the Azan with two-dimensional control, saw limited deployment before the European war ended. It added range correction to the azimuth control of the Azan, allowing the bombardier to adjust the bomb's trajectory in both horizontal and vertical planes. This increased precision further, but also increased the bombardier's workload and the complexity of the system. Only a few hundred Razan bombs were deployed in Europe, though the system would see more extensive use in the Korean War, where American forces again enjoyed the industrial capacity to develop and field specialized weapons for specific tactical problems. The parallel programs for radio-controlled aircraft, Project Aphrodite and its variants, represented a more dramatic application of remote guidance technology. War-weary bombers, aircraft too damaged or obsolete for continued combat operations, were stripped down, packed with explosives, and converted into crude guided missiles. A human crew would take off in the aircraft, arm the explosives, and then parachute to safety, while a trailing control aircraft guided the flying bomb into heavily fortified targets like German submarine pens or V-weapon launch sites. The concept was bold and expensive. Each mission consumed an entire aircraft and risked the lives of the volunteer crew, but it embodied the American willingness to expend resources for tactical advantage. The Germans had nothing comparable, not because they lacked the technical knowledge, but because they could not afford to sacrifice aircraft and crews on what were essentially experimental long-range guided weapons. Project Aphrodite achieved mixed results. Several missions ended in failure when the explosive-laden aircraft malfunctioned or crashed before reaching their targets. Lieutenant Joseph Kennedy, Jr., elder brother of the future president, died in August 1944 when his Aphrodite aircraft exploded prematurely over England, a reminder that experimental weapons carried substantial risks for those who employed them. But successful Aphrodite missions demolished targets that conventional bombing had failed to destroy, proving that radio-controlled aircraft could deliver massive explosive payloads with sufficient accuracy to justify the costs. The program was small-scale and would be overshadowed by other developments, but it demonstrated American willingness to explore unconventional solutions and accept casualties in the pursuit of technical innovation. For the German officers who studied these programs after the war, many were recruited into American intelligence and technical services during the early Cold War. The radio-controlled bombs and aircraft revealed a different kind of scientific culture than they had experienced in the Reich. German weapons development had often been driven by brilliant individuals pursuing theoretical excellence. Engineers like Wernher von Braun developing rocket technology years ahead of its time, designers like Willy Messerschmitt creating jet fighters that represented genuine breakthroughs in aerodynamics and propulsion. But these programs often suffered from insufficient resources, competing priorities, and a tendency toward over-engineering that produced technically brilliant systems that were difficult to manufacture and maintain in the field. American weapons development operated differently. It was more distributed, with multiple organizations and companies working on similar problems in parallel. It was more pragmatic, prioritizing what could be built and fielded quickly over what might be theoretically superior. It accepted that first-generation systems would be imperfect and planned for iterative improvement rather than attempting to achieve perfection in initial designs. And it was integrated with industrial production from the beginning. Weapons were designed with manufacturability in mind, using materials and techniques that could scale to mass production, avoiding exotic solutions that might work beautifully in prototype but could never be built in quantity. This systematic approach to innovation was less visible than individual technical breakthroughs, but ultimately more powerful. The radio-controlled bombs were not revolutionary devices. German engineers examining captured examples could understand how they worked and could have built similar systems if given the resources and time. But the infrastructure that produced 15,000 guidance units in 18 months, that trained hundreds of bombardiers to use them effectively, that integrated them into bombing doctrine and maintained supply chains to keep them operational across multiple theater commands, that infrastructure represented capabilities that the Reich had never possessed and could not have developed under wartime conditions. Klaus Richter, the Luftwaffe officer who had analyzed American bombing patterns, ended up working for American intelligence after the war, translating captured German technical documents and providing insights into Wehrmacht capabilities and doctrine. He spent years studying the American military-industrial system from the inside, trying to understand how a democracy had out-organized and outproduced a totalitarian state that had supposedly marshaled its resources with ruthless efficiency. His conclusions, expressed in conversations with American colleagues, centered on the paradox that decentralization had proven more effective than centralization for managing complexity at scale. The German war economy had been highly controlled, with central authorities directing resources and priorities, attempting to optimize allocation through bureaucratic planning. This worked reasonably well for producing large quantities of relatively simple weapons, rifles, artillery, ammunition. But it struggled with complex systems that required coordination across multiple industries and technical domains. Development programs often stalled due to competing priorities, material shortages, and the difficulty of coordinating specialized suppliers. The Reich's command economy could achieve impressive things through focused effort, the V-2 rocket program, for instance, but it could not maintain dozens of parallel development programs simultaneously, could not tolerate the waste and redundancy that breakthrough innovation often requires. The American system was messier, less centrally controlled, more tolerant of duplication and competition between different approaches to the same problem. Multiple companies developed competing designs for similar weapons, with military services evaluating prototypes and selecting winners based on performance and production feasibility. This seemed inefficient. Why develop 3 different radio-controlled bomb systems when one might suffice? But it created resilience and accelerated innovation. If one approach hit technical problems, others continued forward. Competition drove improvement, with companies innovating to win contracts rather than waiting for central authorities to direct development. And the scale of American industry meant that even losing designs often got produced in quantities sufficient to contribute to the war effort. Richter came to see this as fundamentally connected to American political culture. Democracy was inefficient in many ways, but it distributed decision-making and allowed for disagreement and competition in ways that ultimately produced better outcomes when dealing with complex problems that no central authority could fully understand or optimize. The radio-controlled bombs emerged from this environment, multiple organizations working on similar problems, sharing information but also competing, learning from failures and successes, iterating toward solutions that worked reliably under field conditions. It was innovation through managed chaos rather than through centralized planning, and while it appeared wasteful compared to German efficiency, it ultimately delivered superior results at the scale the war required. The symbolic weight of the radio-controlled bomb extended beyond its tactical effects. In Nazi ideology, technology was supposed to be an expression of racial superiority, of German scientific genius triumphing through pure intellectual excellence. The Reich's wonder weapons, the jets and rockets and exotic devices that propaganda celebrated, were meant to prove that Aryan ingenuity could overcome material disadvantages and reverse the course of the war through technical breakthroughs that lesser races could not match. When American forces not only matched, but exceeded German technical capabilities through systematic industrial excellence rather than individual genius, it undermined these ideological foundations. The radio-controlled bombs suggested that democracy and capitalism, systems that Nazi philosophy dismissed as decadent and inherently inferior, could actually organize human effort more effectively than fascist central planning. American soldiers and airmen rarely thought in such abstract terms. To them, radio-controlled bombs were simply another tool, another piece of equipment that helped them accomplish their missions and survive the war. But in their casualness about weapons that should have been extraordinary, in their assumption that technical superiority was natural and expected, they embodied a confidence that was itself a strategic weapon. The young bombardier from MIT who guided Azon bombs with toggle switches and visual tracking, who chatted about the system as if steering falling explosives through radio waves was unremarkable, represented an America that had moved beyond the uncertainties and insecurities of the Depression era into an understanding of itself as a technological civilization without peer. The B-24 Liberators and B-17 Flying Fortresses that carried these weapons home bore other symbols of American abundance that German observers found equally unsettling. The bomber crews ate chocolate bars and chewing gum during missions, casual luxuries that Wehrmacht soldiers had not seen in years. Their aircraft carried sophisticated oxygen equipment, heated flight suits, and medical supplies far superior to Luftwaffe equivalents. When American bombers were shot down and crews captured, German interrogators often spent more time asking about living conditions and supply systems than tactical information, trying to understand whether the captured airmen were elite units, or if all American forces enjoyed such abundance. The answer, that these were ordinary servicemen receiving standard equipment and rations, suggested resource differentials that made continued resistance militarily futile regardless of tactical competence. The radio-controlled bomb missions continued through April 1945 as American forces overran German positions and the Reich collapsed into fragmented chaos. Bridge strikes isolated Wehrmacht units, preventing organized retreat or reinforcement. Railway junctions were severed with precision that paralyzed supply lines. Command bunkers and communication centers disappeared under direct hits that conventional bombing would have required dozens of sorties to achieve. The cumulative effect was not just physical destruction but psychological collapse, the sense that continued resistance was pointless when the enemy could see everything and hit anything with casual precision. On May 8, 1945, Germany surrendered unconditionally. The radio-controlled bombs had played a small role in this outcome, one tactical innovation among thousands that collectively overwhelmed the Wehrmacht. Their significance was disproportionate to their numbers or the damage they directly inflicted. They mattered because of what they represented: American technological sophistication matched to industrial scale, creating weapons that were both advanced and abundant, deployed not as desperate wonder weapons, but as routine improvements to existing capabilities. They were emblematic of a way of war that Germany could not match, because it required resources and organizational capacity that extended far beyond traditional military virtues. Friedrich Hartmann was repatriated to West Germany in 1947, returning to a country that barely resembled the nation he had fought for. The cities were ruins, the economy devastated, the population exhausted and disillusioned. But already there were signs of reconstruction, much of it supported by American aid through the Marshall Plan. That same abundance turned from destruction to rebuilding. Hartmann found work as a civil engineer, helping reconstruct infrastructure that he had once defended against American bombs. The irony was not lost on him that he now built bridges using American steel and machinery, that his livelihood depended on the generosity of the enemy that had destroyed his country. He kept his wartime observations to himself for decades, rarely speaking about the radio-controlled bombs or the other technical marvels he had witnessed in the war's final months. But in the 1970s, as he watched American spacecraft land men on the moon, as he saw jumbo jets cross the Atlantic in hours rather than days, as computers began appearing in offices and universities, he recognized the continuity, the same systematic excellence, the same capacity to organize complexity at scale, the same confidence that no technical challenge was insurmountable given sufficient resources and talent. The radio-controlled bombs had been an early signal of something larger, a transformation in human capability that the war had accelerated and that America embodied most completely. Klaus Richter spent 30 years working in aerospace engineering after the war, contributing to the development of guided missile systems and satellite technology. He never forgot the lessons he had learned studying American bombing patterns in 1945. That innovation was less about individual breakthroughs than about systems that sustained excellence across multiple domains. That quantity properly organized became its own kind of quality. That decentralized competition often outperformed centralized planning when dealing with complex technical challenges. These insights influenced his work and his teaching, spreading through a generation of European engineers who rebuilt their continent's industrial base and eventually created aerospace and electronics industries that could compete with American firms on roughly equal terms. The radio-controlled bombs themselves became obsolete within a few years, superseded by more sophisticated guidance systems, radar-homing weapons, television-guided bombs, and eventually laser-guided munitions and GPS-directed smart weapons. The principle they embodied, precision through electronic guidance, became foundational to modern warfare, rendering the carpet bombing of World War II obsolete for military forces with access to advanced technology. The evolution from radio-controlled bombs to contemporary precision-guided munitions represents one continuous line of development, each generation building on the innovations and lessons of the previous one, each improving accuracy and reliability, and reducing the distinction between what could be targeted and what could be destroyed. But in January 1945, as Oberst Hartmann stood in his bunker outside Koblenz and watched an American bomb maneuver through the sky, all of this was unknown and unknowable. What he saw was the impossible made real, physics bent by electronics, precision achieved through invisible signals, American power manifesting in forms that traditional military analysis had not anticipated. The bridge collapsed into the Rhine, its span dropping precisely where the bomb directed it. And in that moment of perfect destruction, Hartmann understood that his side had not simply lost a war, but had been outmatched in a more fundamental sense. The Americans had not just more weapons but different weapons, not just greater resources but different ways of organizing and applying those resources, not just technical capabilities, but a systematic approach to innovation and production that operated on scales the Reich could never match. The bomb itself, that radio-controlled 1,000-pounder that struck the bridge with impossible accuracy, was eventually recovered from the Rhine after the war, its guidance system salvaged by American recovery teams for analysis and improvement. The data gathered from that mission and hundreds of others like it fed into next-generation weapons programs, contributing to the Cold War arms race and the evolution of precision strike capabilities that would define military power in the second half of the 20th century. The weapon that had seemed so remarkable in 1945 would be a museum piece within a decade, made obsolete by systems that improved on its principles by orders of magnitude. But the psychological impact endured. German military officers of Hartmann's generation carried with them the memory of being technologically overmatched, of watching their certainties crumble as American innovations rendered familiar tactics obsolete. This experience shaped West German military doctrine during the Cold War, an emphasis on quality and technical sophistication to compensate for numerical disadvantages against Soviet forces, a recognition that modern warfare favored technological superiority over mass, an integration with American military structures that acknowledged where real power resided. The Bundeswehr that emerged in the 1950s bore little resemblance to the Wehrmacht that had collapsed in 1945, but it incorporated the lessons that men like Hartmann had learned through bitter experience, that industrial capacity and technical innovation were as decisive as tactical skill, that wars between modern industrial states would be won by those who could organize complexity most effectively, that American abundance was not a weakness to be exploited but a reality to be respected, and, if possible, aligned with. Lieutenant James Morgan returned to MIT after the war and completed his degree in mathematics. He spent a career at Bell Laboratories working on early computer systems and telecommunications technology, contributing to the development of digital switching and data transmission protocols. His work guiding bombs over Germany was classified for years, and he rarely spoke of it, treating it as one assignment among many in a long technical career, but occasionally explaining network routing algorithms or feedback control systems to younger engineers. He would reference the Azon bombs as an early example of remote guidance and real-time correction, of how simple protocols and reliable hardware could achieve sophisticated results when properly integrated into a larger system. Most of his listeners didn't understand the reference. Radio-controlled bombs were forgotten history, replaced by technologies so advanced that the World War II system seemed almost quaint. But Morgan recognized the continuity, saw how the toggle switches and visual tracking he'd used over Germany prefigured the user interfaces and feedback systems of modern computers, how the radio links between bombardier and weapon anticipated the telecommunications networks that would eventually connect the world. The war had been a forcing function for technical innovation, compressing decades of development into a few years of desperate creativity, and the radio-controlled bombs were one among thousands of innovations that emerged from that crucible. America had won not just through bravery or tactical skill, but through systematic excellence in converting technical knowledge into practical tools, in scaling production to meet strategic needs, in organizing effort across continental distances, and coordinating the work of millions toward common purpose. This was the larger truth that the radio-controlled bombs symbolized, not individual genius but collective capability, not revolutionary breakthroughs but systematic competence applied at scale. The young bombardier with his toggle switch and tracking telescope, steering a bomb through invisible radio waves toward a bridge in the Rhine Valley, was the human element in a vast technological system that extended from laboratories and factories in America across ocean supply lines to bombers over Germany, and ultimately to the target that vanished under precisely placed explosives. One man, one bomb, one mission, but behind it stood the accumulated capacity of American industry and science and organizational talent, focused and coordinated toward the singular purpose of destroying Axis military capability and ending the war. The Oberst in his bunker, watching that same bomb perform impassibly, understood that he was witnessing not just a weapon, but a revelation about the nature of modern power. The Reich had believed that will and discipline and technical excellence concentrated in the hands of a racial elite could overcome material disadvantages and achieve victory through superior organization and fighting spirit. The radio-controlled bomb suggested otherwise, that dispersed creativity and competing innovations and abundance properly organized could overwhelm focused excellence, that democracy's messy inefficiency could produce better results than authoritarian efficiency when facing problems too complex for central planning to solve, that quantity transformed through systematic improvement became its own kind of quality that no amount of tactical genius could counter. In this sense, the radio-controlled bomb was less important for what it destroyed than for what it demonstrated. The bridge that collapsed into the Rhine was one of thousands destroyed during the war. The tactical advantage of precision bombing was real but incremental, but the symbol, the reality of American technical sophistication matched to industrial abundance, deployed casually as if such capabilities were natural and expected, undermined the ideological foundations that had sustained German resistance. If America could build weapons that shouldn't exist and deploy them in quantities that seemed physically impossible, then the propaganda about democratic weakness and capitalist decadence was not just wrong but inversely wrong. Democracy had organized power more effectively than dictatorship. Capitalism had mobilized resources more completely than command economies. The soft and individualistic Americans had proven harder and more capable than the disciplined Herrenvolk, who claimed racial superiority. The war ended not with wonder weapons saving the Reich, but with wonder weapons proving irrelevant against an enemy that could absorb losses and continue attacking until nothing remained to defend. The jets and rockets that German propaganda celebrated arrived too late and in too few numbers, while American innovations, less dramatic but more practical, accumulated into overwhelming advantage. The radio-controlled bombs were emblematic of this difference, representing an approach to technology and warfare that valued reliability and abundance over sophistication and elegance, that accepted imperfection in individual systems but achieved dominance through scale and persistence. Today, precision-guided munitions are standard equipment for advanced military forces, so common that their use rarely warrants comment. Bombs guide themselves to targets with accuracies measured in feet rather than miles, steered by GPS signals and laser designators, and sophisticated onboard computers that make the radio-controlled weapons of 1945 seem primitive by comparison. But the principle remains unchanged: electronic guidance enabling precision that mechanical systems alone cannot achieve. Human judgment augmented by technological capabilities that extend and amplify intention. The bombardiers who steered Azon bombs with toggle switches pioneered techniques that evolved into the remote piloting of armed drones halfway around the world. The same fundamental concept, scaled and refined through generations of technical improvement. And somewhere in that evolution from crude radio-controlled bombs to contemporary smart weapons, lies a truth about America's relationship with technology, about the distinctive ways that democratic capitalism organizes innovation and production, not through central planning or authoritarian efficiency, but through distributed competition and parallel development, through tolerance for failure and iteration toward success, through abundance that permits experimentation and accepts waste as the cost of breakthrough innovation. The German officers who watched American bombs maneuver through the sky were witnessing more than tactical advantage. They were seeing a different way of organizing human capability, one that their own system could not match or counter. The Rhine still flows past the city where Hartmann's bunker once stood, though the bunker itself is long gone, removed in the decades of reconstruction that followed the war. The bridge that collapsed under radio-controlled bombs was rebuilt, and then replaced again as traffic demands exceeded its capacity. Modern bridges span the river, carrying trucks and cars and high-speed trains, linking Germany into the European economy and the global trading system. The scars of war have been effaced by prosperity and time, and few who cross those bridges today know the history beneath them. The moments when individual weapons falling from winter skies demonstrated truths about power and technology that would shape the post-war world. But the memory persists in military doctrine and strategic planning, in the understanding that wars between advanced industrial states will be decided not by courage or tactical skill alone, but by the ability to innovate and produce and sustain operations through superior organization of national capacity. The radio-controlled bombs taught this lesson definitively, and those who learned it, whether German officers like Hartmann and Richter or American engineers like Morgan, carried that knowledge forward into the world they built after the guns fell silent, a world where American power rested less on military force than on technological and economic foundations, where alliance and abundance created security more enduringly than conquest and extraction, where the values that had animated democratic resistance to fascism, openness, innovation, pragmatism, trust in distributed initiative rather than centralized control, proved more durable and powerful than the ideologies of those who had bet on other principles. The bomb that maneuvered through the January sky and struck its target with impossible precision was just metal and explosives and crude electronics, a tool employed for a moment and then forgotten. But the system that created it, deployed it, made it routine rather than remarkable. That system endured and shaped the world. In the confidence of the bombardier steering falling weapons through radio waves, in the despair of the German officer watching certainties crumble, in the bridge dropping precisely into the river, there was a symbol more powerful than the explosion itself. It was the sound of the future arriving, of one kind of power giving way to another, of industrial democracy proving its capacity to organize destruction so efficiently that resistance became futile, and the only rational choice was surrender and reconstruction on terms the victors dictated. And so the war ended, and the world turned, and the weapons that had seemed impossible became routine and then obsolete, superseded by technologies more advanced still. But the lesson remained, that abundance properly organized overwhelms scarcity however brilliantly deployed, that systematic excellence defeats individual genius at scale, that the capacity to innovate continuously and produce reliably and sustain operations indefinitely represents power that no amount of tactical brilliance can ultimately overcome. The radio-controlled bombs taught this truth to those who witnessed them, and through their experience, it became part of the strategic understanding that shaped the Cold War and the global order that followed, not through ideological persuasion or cultural influence, but through simple demonstration of capability, bombs that steered themselves through invisible signals, bridges that collapsed under precise strikes, a nation that deployed the extraordinary casually because its capacity rendered the remarkable routine. This was America's revelation to its enemies in the war's final months, delivered on electromagnetic waves and demonstrated through precision destruction, that you cannot compete with a system that makes the impossible ordinary through sheer abundance of talent and resources and organizational excellence. The bombs fell true, the bridges collapsed, the war ended, and the world learned what industrial democracy at full mobilization could achieve when technical sophistication met continental scale and systematic dedication to practical results. In this, the radio-controlled weapons were less important than what they symbolized, not individual devices but the entire system that created and deployed them, not tactical advantages but strategic inevitability, not wonder weapons that might reverse fortunes but routine capabilities that confirmed what the outcome would be, and always had been since the moment America's industrial might turned fully toward military purposes. The conclusion had never been in doubt, not really. The radio-controlled bombs simply made it visible, made it undeniable, etched the truth in broken stone and twisted steel, and the stunned silence of those who watched precision emerge from chaos through the miracle of electronics and organization, through the casual confidence of a nation that built the future while winning the present, that deployed technologies casually that others would have celebrated as ultimate weapons, that won through abundance and excellence rather than genius and desperation, won because the system worked, because the principles underlying democratic capitalism proved more powerful than fascist organization when tested at the scale of total war, because the bombardier with his toggle switch represented something more formidable than any ideological Superman, something rooted in pragmatic excellence and systematic capability, and the quiet confidence that comes from knowing that your society can build anything it needs to build, solve any problem it needs to solve, sustain any effort that survival requires. This was the revelation that radio waves carried to German observers in the war's final months, not propaganda but demonstration, not claims but proof, not ideology but simple truth made manifest in the arcing path of bombs that should not have been able to maneuver but did, that should not have been so numerous but were, that should not have been deployed so casually, but embodied an abundance so complete that the extraordinary had become routine. And in that routine excellence lay the true victory, the one that would outlast the tactical outcomes and strategic settlements, the victory of system over ideology, of pragmatic capability over theoretical sophistication, of organized democracy over authoritarian control. The bombs fell, the bridges collapsed, the war ended, and the world learned.